The conditions, guess what? The same three conditions again. Okay. Is it random? 10%, meaning is the population at least 10%, is the population at least 10 times the size of the sample? And then large counts, this one's different from what we've seen previously. This large count one says that all expected counts must be at least 5. So the normality, so to speak, that we've looked at before is different. The large counts now, it's not N1 times P1 has to be greater than or equal to 10. Now it's expected counts that are going to tell us if it's large enough. All expected counts must be at least 5. So these are the conditions for chi-squared. Suppose that these conditions are met. If we want to perform a test, the null, as we saw in the previous example, the stated distribution of the categorical variable in the population of interest is correct. What in the hell are they saying? Okay, so they're saying here that the null is that the distribution is as claimed. It's as the researcher claims it is, or what we think the answer is going to be. Okay. Then how are we going to calculate degrees of freedom? Well, we've always said before, degrees of freedom was n minus 1. Well, that's true here, but notice that in the book is going to talk about K. K is the number of different categories. So you can think for chi-squared, you can think of it as n minus 1, but we're going to use, instead of n minus 1, we're going to use K minus 1. I do not like that yellow color at all. Let's get rid of that. That's ugly. Let's try see what maroon looks like. Well, if we use a pencil, it'll usually work better. That's still yellow. Let's try this one. K minus 1 degrees of freedom, where K is the number of categories. So if we think about the dice, there was 6 different things that could happen. If we think about the M&Ms, there were 6 different things that could happen. So both of those examples that we've looked at thus far would have 5 degrees of freedom. All right, so what does the distribution look like? Very skewed to the right. Okay. What are the conditions? Random. Did they tell us or not? 10% is the population at least 10 times the size of the sample. And all expected counts are 5. That's the new condition that we haven't met yet. Okay. Well, let's take a look at a problem here. And let's see if we can put all this together. In his book of Outliers, Malcolm Gladwell suggests that hockey players' birth month has a big influence on their chance to make it to the pros. Specifically, he thinks that players born in January would be competing against players up to 12 months younger. The older players tend to be bigger, stronger, more coordinated, hence get more playing time, more coaching, and have a better chance to be successful. So are more of the pro hockey players born in January through March than any other month? To see if the birth date is related to success, we took a random sample, random, that's going to be good for us for our condition, of 80 NHL players. And here is the data for those 80 players. All right, so do these data provide convincing evidence that players are not uniformly distributed across the 4 quarters of the year? So what is our null hypothesis? That there is no difference. So the birthdays of NHL players are uniformly distributed. So guess what the alternative is going to be? The birthdays of NHL players are not uniformly distributed. Okay. So we're explaining what we want to test. Since they didn't tell us, we're going to have to assume that alpha is 0.05. Okay. What's our plan? What kind of test are we going to run? Oh, this is a chi-squared. They call this goodness of fit test. We're going to see another type of chi-squared test here in a minute. So anytime we have one categorical variable such as this, we'll call that the chi-squared goodness of fit test. All right. So that's what we're going to do. We want to test that. Are we allowed to do it? Well, random, they told us. We have to assume there are more than 800 NHL hockey players. Since our sample was 80, then for the independents, there are more than 800 NHL players. I don't know the answer to that, but that's the assumption we have to make for the 10% condition. Okay? And then for the large count condition, remember that condition says that no expected count can be less than 5. So if they're uniformly distributed, then we expect 25% to be in the first quarter, 25% to be in the second, 25% to be in the third, and 25% to be in the fourth. So this total of 80, we're going to multiply that by 25. And that's going to give us an expected count of 20. So large count, yeah, all expected counts are above 5. Or we could say something like all expected counts are 20, which is greater than or equal to 5. So what are we going to do? We're going to test to see if hockey players truly have a uniformly distributed birthday. Or are professional hockey players more likely to be born in the first quarter of the year versus the rest of the year, like this researcher suggests? Now we have to do it. So what are we going to do? Are we allowed to do it? Now we're going to do it. So we need to calculate the chi-squared test statistic. So let's take a look at calculating chi-squared. So chi-squared equals observed minus expected squared divided by expected plus the next observed minus expected squared divided by expected plus the next observed minus expected squared divided by expected plus the next observed minus expected squared divided by expected. So this is 144 over 20 plus 0 plus 16 over 20 plus 64 over 20. So that's 226 over 20. Which I believe will give us 11.2. 226 divided by 20 is 11.3. Maybe I made a mistake in my addition here. 144 plus 16 plus 64 equals 224. So that gives us a chi-squared of 11.2. How many degrees of freedom does it have? Well, it's one less than the number of categories. So this problem is going to have, there's 4 categories. It's going to have 3 degrees of freedom. Now let's find our p-value. This is something we haven't looked at yet in this unit. We're going to go grab table C, the chi-squared table. 3 degrees of freedom and a chi-squared of 11.2. So we come across here at 3 degrees of freedom. And we go across till we trap 11.2. Oh, 11.2 is in between 9.84 and 11.34. So my p-value is between 0.01 and 0.02. 3 degrees of freedom, 11.2 falls in here. So between 0.01 and 0.02. So my p-value is bigger than 0.01, but smaller than 0.02. So clearly it is less than the stated alpha or the alpha level of 0.05. If p-value is less than alpha level, the data is statistically significant and we reject the null. So what do we conclude? We have convincing evidence that the birthdays of NHL players are not uniformly distributed. We have convincing evidence that the birthdays of NHL players are not uniformly distributed because our p-value here is smaller than our alpha level. So I didn't write the conclusion out, which I probably should. That's probably the most important thing. Okay? Because the p-value is less than the alpha level, we reject the null. The data is statistically significant. We do have convincing evidence that the birthdays of NHL players are not uniformly distributed across the 4 quarters of the year. So we just did the entire process for a goodness of fit test. This is when we are looking at a one categorical variable. We can run this chi-squared goodness of fit test such as we have done right here.